Right, so today's lab is on capacitors. Let me share my screen and we'll get started. Okay, here. It's a rather, um, it's a shorter lab than a lot of the previous ones. It's only worth 55 points. I'd say it's a pretty short lab. There's not much um, that you're going to be doing. There's a lot of um, sort of conceptual things with this lab. It might make it difficult. Um, I think I've had a lot of people finish it within an hour or so. So if you do stick around, you could have a good chance of finishing it right away. But let me get into the instructions. So up at the top, same as normal. Remember, we're going to need to write our own introduction near the top. I think there's even a spot for it now uh, in these instructions. So always an introduction and always a conclusion at the end. We're going into PhET simulation. It's going to be similar tools from last week. Let's go here. You'll see this page. And for the first, I want to say half of the lab, we're going to do this capacitance section. So let's click on capacitance. And we have a lot of familiar tools for us. Um, we're only going to be able to measure voltage, and we should, by this point, know how to measure voltage of something in a circuit. So we need to measure across whatever we want to find the voltage difference of. So if I wanted to find the voltage difference or the potential difference across this capacitor, I'd have to put one probe on one side. I could put on this black dot right here, and I'd put the other probe on the other side, wherever on this dot. Sure. Could also do the wires. Um, that's up to you. For this lab, we're going to be uh, charging up this capacitor with this battery. See, it's hooked up to the battery, and feel free to mess around with this. We're going to see how charges flow and current direction. So right now, there's no arrows on the wires, so there's no current in this system. Let me go over to the instructions. So for the first bits, it's just sort of, small measurements and some qualitative things. What do you observe? Um, Later on, we're going to be subtly changing a thing about the system. So, um, you know, let's go back to it. So once it's charged, we're going to raise and lower this. Oh, I think another thing, the big thing to make sure about this is all of these boxes up in the top right are filled in. So you need to click on electric field right here. So those are all filled in. And then once this is charged at the point the instructions say to, later on, you're going to be manipulating sort of the distance, and you're also going to be manipulating the size of the plates and seeing how does the charge react, how does the current in the wire react. Um, okay. The second part will be disconnecting this charged um, capacitor. So you see these little dots on the top. That'll just let you sort of unhook it from the circuit. So right now it's hooked up, but I can disconnect it. That's what this is showing. Okay, and this it mainly is to show you or to help you out with this next following section. So that's sort of just a small disconnecting section. We're going to be hooking it up to a light bulb. So that's where we're going to switch to the other uh, tab. It's down here at the bottom. or you could refresh the page and just click on light bulb. Okay, so in this system, we're going to be charging up the capacitor and it will then hold some charge. And I'm just going to do a very small amount just to show you. So very small, come on, sure. And I could disconnect it and then connect it to the light bulb and see how does it react. Let me just do a small one, so like that. And what happens? This is a very qualitative lab today. Right, so you're going to be following these instructions a bit more closely. I was just giving a little example. And then at the bottom, discharging, at the bottom, there's this challenge section. So for the people who do stick around, I might be a bit more vague in trying to help you with these. So trying to let you guys, brainstorm on this one. Right. And then at the very, very end, conclusion, like always. Okay. I think that is it. So it's a rather short lab. We don't have to do much, but it's a lot of conceptual sort of, stating what you observe and then trying to reason out what is happening. Okay, so let's go to the instructions here. Are there any questions on this before I go over to the notes? Actually, I'm gonna do that. If you do have a question, just say so. Okay. So capacitors. What's a capacitor? Well, a capacitor, the symbol is just this. It's two plates together with some lines coming out of it. And that actually does describe it pretty well. Let me see if I could find a picture of it real quick. So in a capacitor, the charge will be stored on these plates, and you can use this sort of as a place to hold charge for when you need it later. And in a circuit, a capacitor might look something like this. Let's go like this. So in a capacitor, they have these little tubes. But what's going on inside of it? There's this sort of cinnamon roll, sort of like it's a twisted metal. It has been these two long strips of metal. They're separated by like some paper or maybe might be some rubber. It's these two little thin pieces of metal that are twisted together, and they can store charge. So that's a good thing to write down. Capacitors store charge. What good is that for? Capacitors store charge. So why would we need a capacitor when we have like a battery? Batteries just produce, a lot of charge over a long period of time. Why would we need a capacitor? Well, sometimes you don't want to, fully use up an entire battery for, a simple process. If, say, for example, like your windshield wipers, they are going to be there's a capacitor in your windshield wipers in your car, and it takes time for the capacitor to fill all the way up with charge, and then as soon as it's full, it will discharge, and your windshield wiper blades will, you know, then be activated and go. So there are different sizes of capacitors, and that's why you could choose different speeds for your windshield wipers. It's a bit more technical than that, but that's sort of the very, very, very basic essence of it. So capacitors store charge. They're charge sponges. Let me draw a capacitor better than this one up here. So this is like the circuit diagram over here. Let me make another one. It's a bit better or bigger like this. What's actually going on inside of a capacitor? So there are these two strips of metal, and it's disconnected. It's not connected to a circuit. It is neutral. Neutral charge. So what that means is, there's no uh, charge inside of it at this point. There's an equal number of positive and negative charges in both sides of the capacitor. So neutral charge, there's no such thing as like well, I mean neutral in that there's an equal amount positive and negative. Okay. So there's a neutral charge and a disconnected capacitor. Then when we connect it to a battery, let's take that same capacitor and hook it up to a battery. What's going to happen? So there's a negative side, there's a positive side of the battery, and there we go. So the large side is positive. What's going to happen to, let me draw these charges again. What's going to happen to the charges that are on this capacitor? There's going to be a current because we've learned previously there's a current from a battery, and typically in sort of the previous labs, I may have said that there's a current flowing out of the positive side this way, and it'll flow through the circuit like that. Now this was a positive current I was referring to, and that's sort of maybe your lecture instructor has already gone over this, but um, that's sort of the I don't want to say lie. That's sort of the big thing that we have to address. Kind of like a lie. So there is this. It seems like a positive current flowing this way, and it'll go through. For example, let me just do one that's not a capacitor. So we've seen this. This is my previous example, and I may have drawn a current going, through like that and back to the battery. What's actually happening is, let me draw it again. What's actually happening inside of a circuit is the negative charges, this is still positive, the negative charges, the electrons inside of the wire are flowing that way. And that's sort of why in a lot of these programs you see this electron uh, function, and they're flowing opposite of the conventional current. So this is conventional. These are conventional currents or conventional flow. This is electron flow. Now, why are these different? It's because someone a long time ago made the mistake of thinking this was the thing that was actually happening. That person was Benjamin Franklin. And it is true. He, um, at that time, it wasn't known that the electrons were the ones that were actually moving in the circuit. At that time, electricity was being studied more and more. It wasn't quite, everyone wasn't quite familiar with it, especially what, an electron was. So there had to be a decision, and Benjamin Franklin looked at this and said, well, it looks like positive current is going out of this. And so I'm going to say there's a positive direction this way, when what's actually happening is the negative electrons are flowing this way. In any case, jumping to right now for this capacitor lab, what's actually happening. So now let's look at the electrons specifically. So there are charges on these plates, positive and negative. The protons of a metal are positive, the electrons are negative. So protons, the positive, electrons are the negative. What's actually happening, we have this positive side of the battery. When we hook it up to this circuit, the electrons on this side of the capacitor, they can then feel this large attraction to that positive side of the battery. It's much stronger than that of the positives on the plate. So the electrons on the plate begin to move outward and to this side of the battery, to the positive side. At the same time, go out and they'll go all the way to the battery. At the same time, one electron will reach the battery, and there has to be a conservation of charge happening in this battery. So one electron is kicked out, and it's right next to this negative side of the battery, and it doesn't want to be there at all. So it would rather get very far away from this negative side. So it will go that way, down the wire, and it will eventually be placed on this side of the uh, capacitor. So um, electrons on a plate are attracted to the positive side of the battery. Okay, so that's how and that's why there's this sort of flow, even though there's too many arrows, even though there's nothing connecting this circuit. It's not physically touching both sides. Okay, so let's go to what's happening now over here. Let's say it's been however long, negative, positive, and you can see that's only the negative charges, you have to remember only electrons are the ones that are moving in anything. So the electrons are free to move as they wish. The protons of an atom have to stay where they are. So what we get is a bigger sort of separation of charges as more and more electrons are taken away from this side and attracted to the positive side of the battery, and more electrons are deposited onto this side of the capacitor. Okay, and that's sort of the intermediate step. What we finally get to is a case where that like that. What we finally get to is a case where near all of the electrons, not necessarily all, there's this big separation. 5, 6, 1, 2, 3. There's now this big separation of charge on this capacitor. Let me go like that. And it gets to the point where the electron sort of flow that was traveling down, now it gets to this point, and these charges are so separated that it feels it's an electron. It feels an equal attraction to the battery. It wants to go that way. And it feels an equal attraction, equal the battery to this side of the plate. And so since those two forces are equal, it doesn't move. I could just leave this. It doesn't move, and that's how this sort of separation stops. And that's when the electrons stop and the current stops also, because there is no more movement in the wire. So once the force of attraction of is equal positive side of the battery, the electron flow stops. Okay. All right. So what else can we say about this? At this point, there's this sort of, just buildup and separation of charges. Let me take this picture and I'll put it down here, or people might still be writing. Let me put it right here. One, 2, 3, 4, 5, 6. Okay. An interesting thing, or something you should know, is that whatever amount of charge was measured in coulombs. So since electrons have left and now there's this overwhelmingly positive charge on this plate, let's say it's positive 6 coulombs. The unit of charge is coulombs. Remember, that was a 1-for-1, so one charge came off and another charge, and one charge was deposited onto this side. So this has -6 coulombs. All right. What else? There is, once this capacitor is fully charged, and that it stops, there's no more current flowing in this wire. Once it's fully charged, the potential difference across the two plates, V, is the same as the potential difference of the battery. I made it sort of represented by having them right above each other. Okay. So potential difference okay. Let me move this over. In the lab, we're given the equation Q equals CV. Q, that is the amount of charge on one plate. Actually, let me, before I put definitions on this, let me say for the lab, we're specifically interested in rearranging this equation. So let me write this with C equals, so it'd be C. So C is the capacitance of the capacitor. C equals Q over V. So amount of charge on one plate. And V is, potential difference. And that's voltage. Okay. So now let's do, what else did I want to do? Almost done. Let me do one more little example or just picture. Let me do like a three-dimensional picture. So remember, these are just like strips of metal or like plates. So let me do like, okay. So positive side of the battery is right there. And it's connected to these two large metal plates. And on these large plates, there's this sort of, there's a lot of space available for charge to collect. So let's see, I'll just show that by putting like a lot of charge on the plates. A lot of charge. And the opposite is true. If I have two very small plates, I can't fit as many charges on the plates. So let's say like there's only two. So what we see is this sort of relationship with a let me see. So I'll write this C capacitance. I should have wrote capacitance. Capacitance is a capacitor's ability to hold on to charge. So how well can it store charge? So how does that change when we look at these two examples? Well, Q over V. So for this one over here, it stores a lot of charge. So, that Q on top, that should be very large. Does that mean that the capacitance also increases? Not necessarily, because since there's a lot of charge, there's going to be a big potential difference between the two. Remember, it's the strength of the charge and how close it is to one another. So this V on the bottom of this fraction is also very large. Let's look at the other little example. So since there's a small amount of charge on these small capacitors, it's a small amount of charge. And there should be a small amount of potential difference. So since these ratios, Q over V and Q over V, since they change equally, that means that the capacitance doesn't change. So how would we be able to change the capacitance? Well, that's where we need to we need to use that slightly different formula that's given in the lab for capacitance. We can't just rely on how much charge is on it and how much the voltage across it. That's helpful in some cases when we quickly need to know capacitance. But if we were looking to find a very specific capacitor with a very specific capacitance, we would need to use this formula. That's fancy K, that's kappa. I think that's epsilon naught A over D. So first thing is, I'll get out of the way. These are constants. These are constant values that are given in your lab, and they're sort of like what I was saying. So they're sort of like how well can a charge be stored on the capacitor. This kappa is the dielectric constant, and the epsilon naught is the electric constant. These are just numbers, so for that sake, I will let you look that up in your lab. But we have right here A, that's the area of the capacitor. How big is it? How big are these plates? And this D, that's the distance between the two. So just increasing the distance can change the capacitance of a capacitor, or getting them closer together. Okay, so quite a bit. Any questions on these notes or the lab? Okay. Since it is fairly conceptual, and I don't think there are really any divided parts, I'm going to say if you want to stick around and work on it, I can help you. I'll be here until everyone leaves. But if everyone else, if you want to work on it later, that's fine. Let me open breakout rooms for people who do want to stick around and work on it. Say I'll do that.